Okay. Thank you, everybody, for being here. We are here with Edward, and we are, we'll see how to do Python packaging on the enterprise. Thank you, Edward.
Thank you. Good morning. Thanks all for getting up on this last day of the conference. My name's Edward Easton. I'm an Aussie freelancer working in London at the moment. I've been a Python coder for about 10 years. I'm currently contracting for an algorithmic trading firm in London. Now, I'm not much of a Trekkie, so to speak. I'm more of a Star Wars kind of person. But I am wearing the traditional red shirt of the disposable crew member, as you should all know, being Trekkies here. Okay, so why the Star Trek jokes? Usually when people think enterprise in computing, it's like expensive, bloated. We paid far too much for a piece of code that didn't actually work, and we had to spend another year making it work. In this case, I'm not really going down that route. I mean more big teams, lots of packages, lots of people working on big code bases all of the time, things changing all over the place. And also the sense of a more restricted environment. So you've got paranoid sysadmins who don't let you put compilers on the boxes and all that kind of stuff. Okay, so PackageLib, that's what this is about. It's a library that we put together and open sourced just very recently. Why did we write this? The reason we wrote it was this look here. You know that look that people give you when you're digging yourself into a sort of conversational hole? Basically, this is a look I got from my chief science officer when explaining how to do Python packaging as of about 2 years ago. So we were onboarding Python in a big quant shop, basically, as the main language for research as well as trading, and explaining that we needed one tool to install this kind of package, a different tool for that kind of package, and this other thing to uninstall. It wasn't very pretty. So he basically just said, please go and sort this out. So what sort of problems did we have that we had to solve with this library? And what were the goals of the project? So we had lots of developers coming on board who were not necessarily new developers, but new to Python. So a lot of Java guys that were coming in expecting something sort of like Maven. So we had to basically unify what was a pretty inconsistent command set for managing virtual environments, creating projects, documenting code, that kind of stuff. We also had to improve on improving the dependency resolver. When you have lots of code, and we need to be able to treat in-house packages different from external packages. And also handle quite complex dependency graphs when you've got lots and lots and lots of packages. And sort of slightly different to normal Python shop workflows where we had internal releases, where we had researchers building trading code and technologists building code. They have to release it, gold standard, and then more code was built on top of it. So it's this kind of internal release process. So a quick overview. Originally, PackageLib was 3 different packages. To make it easier on the compliance team for getting it signed off, I squished them into one. I may actually split this up again because it is somewhat monolithic at the moment. But basically, the main section is the PackageLib code, which is the tools for managing virtual environments, managing source checkouts, running tests, building all your code, uploading it to PyPy, that kind of stuff. There's PackageLib.testing, which is a suite of testing utilities. So this is testing utils, a lot of py.test fixtures for working with services, working with databases, special stuff for working with web apps, hooking up web drivers, and lots of tools for py.test. And also there's the batteries included project template, which is just the PayScript template for generating PackageLib-enabled packages. Now, because we're working in an enclosed environment, we've got to take some shortcuts. So currently, as it stands, only works on Linux. Only works on Python 2.6 and 2.7, and the VCS support has only been tested with Subversion. I know, shock horror, big banks are like that. We also got to make some opinionated decisions. So we only work with Python eggs, and we don't work with source packages. And we use py.test, because py.test is awesome. Why do we use eggs? Basically because we wanted to have binary support. When you've got lots of packages in a build server that's continually burning away, having to recompile things over and over again is a massive waste of time. So Python eggs is the way forward with that. But don't worry, now that it's open sourced, we can basically fill in the gaps. So to explain a little bit about the architecture of packaging, I'll give a very short and very simplified history of Python packaging. So in the beginning, there was man, and man gave us package info and distutils and setup.py and all those things. Then man became a spacefaring race, We got setup tools, which gave us easy install in the egg file format. Some good dependency management. And man ran into the green-blooded Vulcans. So setup tools was forked, distribute was born. It was a bit more active development, a few less bugs, which was good. Then along came the marauding Klingons, which was pip, which is the new hot tool on the block. Gave us a good API and the ability to uninstall packages, which is always nice. But don't forget the clever Romulans. We've got zc.build out here, who have quite a good dependency resolver, really great build recipes. So where does packagelib live? Kind of here. So we basically picked the aspects of all of these tools that we wanted to use. It's primarily based on distributes API. And it sort of unites everyone into a grand federation of planets. Why didn't we use pip? Again, like I said before, pip, at the time when we were doing this, pip didn't support binaries. So it was kind of, that was the start and the end of it. If I was doing this the second time round, I would have used pip and just forced it to use binaries or made changes because setup tools API is truly horrendous. In the meantime, setup tools and distribute have merged, but this is after packagelib was built, so that's something to deal with in the future. Okay, some technical details now. I'm going to go into things about the configuration. So packagelib, originally it was a whole bunch of hard-coded internal configuration. This has been ripped out, and we've made a configuration system which uses standard INI format. You need to know some stuff about your company. Things like your PyPy server address. Why wouldn't you just use the normal outside PyPy server? Well, in a company it's good. You don't necessarily want to release all your code to the internet, so having an internal PyPy server is good. There are lots of good implementations for this. Mr. Krekel's excellent DevPy server is a good example of that. You need to know things about how to identify your in-house packages, like your namespaces, things like Jenkins and Hudson servers, test directory layouts, all that kind of stuff. It uses standard INI format as designated by the packagelib config environment variable. So as you have different environments, you can have a development environment, CI environment, your production environment. You can swap your configs around. Within the file itself, it also does environment variable resolution. So again, as you swap your environments, you can change the configuration of your system. If you want to know what the config is at any given time, there is a setup.py target called setup.py config, which will print it out for you. Now, I'm not going to go through all the individual settings here. Rather, I'll point them out as I go through the features of the library. Okay, so let's grab some water. Please tell me if I'm speaking too fast, by the way. Okay, so I'm going to go on to the package configuration itself. Now, one of the things that we didn't like about the standard packaging system was how all of the configuration was inside the Python file. Not so very good for downstream tools. So we moved everything out into the setup.cfg file in a metadata section. And this is sort of looked up at runtime. I was quite pleased that we actually came up with exactly the same format that was in DistriTools 2 in a completely separate train of thought. So this is quite good if you have things like release tools which need to parse and update your version numbers and whatnot for doing your release tool. The upside of this is that your setup.py is now essentially empty. So much like setup tools, you would import setup from packagelib and run the setup method. The caveat to this, of course, is with C extensions. If you've got C extensions in your packages, you still have to define them in code. It was slightly more trouble than it was worth to make an ini file format version of C extensions. But if you want to do it, feel free to send me a pull request on GitHub. Okay, so I'm going to look at package names and versions now. So this little diagram shows a few of the various flavors of packages and what sort of version schemes they support in the kind of packagelib world. So we've got in-house packages and we've got third-party packages. So third-party packages only support released versions. You shouldn't be using dev versions of third-party stuff. Your in-house packages can be either source code checkouts, development versions, or release versions. So it's all very PEP 386 compliant. So here's some examples of the sorts of version numbers you have. Source code doesn't really have a version number. It's just whatever your current source code check is. So how do we identify an in-house package versus a third-party package? Okay, so in your packagelib.ini file, there's a section called namespaces. Now, the Zen of Python says namespaces is good, so this is how it's done. It's basically a straight string comparison. If your package name starts with any of the things in your namespaces section, then it's an in-house package. Simple as that. Okay, so next I'm going to talk about dependency resolution, a subject very dear to my heart. So ostensibly, when you a package that provides a command called pyinstall, which is kind of like easy install, but by default it can work in either two modes, release or development mode. By default it works in release mode. So when you go pyinstall a package, it's in release mode. Pyinstall --dev, it's in development mode. Or setup.pydevelop, also in development mode, because you're obviously developing code. When it's doing dependency resolution, it has a backtracking resolver. I'll go on to this a little bit later, but it's to solve a rather tricky problem you have when you often have lots of packages and lots of different requirements. Another thing that it does is when you have build target requirements, for an example, if say, for example, you're building Sphinx documentation using the setup.py build Sphinx target, instead of having to have that installed before you run it, all of that stuff is sort of lazily loaded. So if you go setup.py build Sphinx, it'll then install Sphinx for you if you don't have it. Just a sort of a time-saving thing there. Okay, so now some of the workflows in development mode. So in development mode, if you've got a source package, it'll leave it alone. Basically, source packages are sort of sacrosanct in the whole kind of package and version world. It sort of leaves them alone, assumes you've checked out a source package, you know what you're doing. In-house packages, it'll go to the latest development version. Third-party packages, they'll stay on the released version. So like I said before, if it's third-party, it sticks on release all the time. You can always override this behavior, by the way, if you pin stuff in your as a version requirement, a specific, say if you wanted a dev version of something third-party, you go that version equals that development version. That'll be fine. When we're in release mode, nothing much changes. Source code remains being left alone, and in-house and third-party packages now always use the latest release version. Okay, so the workflow of the pyinstall command itself. As expected, if it's not installed, you'll get the latest version. And then it'll repeat the process for all of its dependencies. If it is installed and it's a source code checkout, it'll update your source code for you. And then it'll repeat the process for all of your dependencies. If it's an egg file, it'll throw away the egg, get the latest version, and repeat for all the dependencies. For all of these stages, once it's finished, it'll clean up your site packages directory. So what this means basically is that it'll actually, if there's eggs in there that you're not using, it'll delete them. Now, why would we do this? Because disk is cheap these days. Well, yes, but when you've got really big file system, lots of users them, file systems can be quite expensive to back up off-site in big companies, and lots of redundant copies of little files are really not good, and I scored an awful lot of beer with the Linux team when we implemented that. So yeah, basically pyinstall does different things depending on the state of your environment to sort of simplify the command set that people have to learn. Okay, back onto dependency management. So here's a sample dependency graph that I'm going to use to explain one of the resolution problems that it does. So the arrows here denote I depend on you, and the little code snippets are the setup.cfg sections which denote the requirements of what it is. So the ones at the bottom, he requires acme.bar and acme.baz with no particular version, and so on and so forth. Acme.baz up here requires a specific version of acme.clux, the one on the left doesn't. So before, when I mentioned the diamond problem of dependency resolution, that's this one here. So when dependency resolvers work, they have to work their way around a graph of requirements, not packages, requirements. A requirement is this bit here, where it says, I require this package at this version, or any particular version. So the diamond problem here comes in when it moves around the left-hand part of the graph first. So for example, okay, it gets acme.foo, and then it goes to acme.bar, and then it says, I just want a version of acme.clux, I don't care which one it is, so it gets the latest one, which in this case is 1.3, and then it picks up its dependency, acme.waldo. Okay, we've done with that path, around the other side. Acme.baz, I need acme.clux version 1.2. Oh, we've already got 1.3. That's a conflict. Stop. Now, that's not a great solution, and that's currently what easy installed is, or at least is what it did 2 years ago. Because at the end of the day, 1.3 came from acme.bar, which didn't actually care which version it was. So what packagelib does is it actually backtracks. It goes back and it says, well, hang on a minute. my requirement is more specific than your requirement, so I'm more important than you. So it goes back and it throws away, it unwinds that part of the dependency resolution. So it throws away acme.clux 1.3, and it throws away acme.waldo 3.0, and it starts back again at this side. So it picks up the slightly older version and a slightly older version of its dependency. It does all of this using what's called requirement specificity. Specificity. I always have to say that like 3 times. So a pinned requirement at the bottom is more specific than a version range, which in turn is more specific than an unpinned requirement. And that's how it orders basically the different requirements, and it plays them off against each other. So why all the bother with this? This is all quite complicated and stuff. Basically, if you make it really easy for people to make packages in your organization, they're going to make lots of them. They're going to make tons of them. There'll be packages with 1 line in them, and that's still going to be a good thing. So to help with all of these package management things, there's a command called py-depgraph, which comes along, which basically draws your dependency graph, uses graphviz by default. It also supports ASCII art if you've got one of the Perl dependencies installed. That's quite useful. Sort of color codes it for in-house versus external as well. Okay, another little feature. So if you're on the holodeck, your reality is slightly different from normal. You might not have all of the freedoms that you normally do in regular reality. What I'm trying to get to here is, again, back with the big file system thing, having lots of redundant copies of things is not a very good idea. So when we're developing in normal open source form, we've got lots of virtual environments, and every virtual environment has a copy of everything, which is really useful. But having lots of copies of things is not very fun for big. NFS doesn't basically perform very nicely at all. So in your package.zip.ini, you can define and install a search path. What this does is allows you to put unpacked versions of egg files, which at install time, instead of actually copying them into your site packages, it'll just egg link them, much like it does when you do setup.py develop. So just exactly the same as it does with that. It creates an egg link onto these directories here and then runs the post install steps. And that's another disk space saver as well. Okay, some more features. There's a little command called py-checkout, which allows you to check out files by name. This is useful if you've got about 4 or 5 different repositories in your organization and people can't remember where your code is. The way this works is it sort of Shanghai's part of the package metadata, in this case the homepage section, which points to your the address in your version control repository for that particular package. This gets written into that bit of metadata at runtime when the package is built. It looks at your current source code checkout, it figures out where in the repository is, and writes it into the package metadata that gets built into the egg. When you run py-checkout some package, it queries your PyPy server, and then finds it, checks out the code in your current location, and sets it up in the environment using setup.py develop. That's quite a nice little time saver too. Okay, so the plat tool, not greatly named, I must say. When you've got lots and lots and lots and lots of packages and your teams have been making lots of things, it's quite nice sometimes to be able to bundle them all together. So this came from the idea of working with IPython and NumPy. They had this really nice concept called PyLab, which is the sort of IPython, Matplotlib, and NumPy little working group. So when you've got lots of packages and you want to sort of bundle them all together, much like the Borg, they assimilate them. You can create these platform packages. Technically, they're not much different from just another package which has dependencies on other ones with no real code in it. But we found it quite useful if you have a team of people who are working on a particular subject material and they've got a set of packages which make up their development world, and you've got someone moves into that team, they want to easily be able to set themselves up with all those packages with the minimum of fuss. So we came up with these platform packages. There's a little tool that comes along with the thing called plat, which lists and manages these platforms basically. Again, it's configured in package.ini. You just list the packages in your ini file, and that's how it works it out. So there's a little tool called plat. It's loosely based on the VCS command line. So you go plat info, and it tells you what your platform packages are, and any other source checkouts you've got. There's a quick summary of the help file. So you can do plat use, and then you use that platform. There's plat up, update your platform, plat info, plat versions, what are the versions, etc., etc., etc. Okay, so let's move on to tests, because we like tests. So there's a setup.py target called Python setup.py test. What this does is it kicks off py.test under the setup.py process or in a sub-process, depending on how you want to run it, with a few sensible defaults, with verbose output and code coverage. If you haven't got your test stuff installed, it'll go and get it, install the test requirements, and then run your tests. Test discovery works much the same as usual, so you can have different layouts. So some people like to have their tests next to their code. Some people like to have their tests in a separate directory. It will work with either. You can change the name of the directories where the tests get found from your packagelib.ini file. You notice there's some subdirectories here, unit and integration. This allows you to sort of subdivide your tests into different components. So unit tests go here, integration tests go there. And there are command line options to kick off just the unit tests or just the integration tests. There's ones for regression tests as well. There's also a command line target for running just the doc tests. Another nicety of this is when it's running under Jenkins or Hudson, it'll detect this and change the output. So instead of giving you terminal output, it'll generate the XML files for coverage, JUnit, and PyLint. So this works when you're running under Jenkins with like the violations plugin and those sorts of things. Another bit of test nicety is this little command here, ext gcov text. Now, I didn't even know you could do this until one of the clever guys at the company where we've developed this. Basically, this allows you to get code coverage on your C extensions. This is absolutely awesome. I didn't even know this was possible. So it kicks off this project called gcov-r, which does lots of clever stuff. And basically allows you to get code coverage on C extensions. Very, very cool. Okay, moving along. Project templates. So packagelib needs to have a few little bits and pieces in place for projects to work with it. So there's a template called pymakeproject. You give it a name. It'll ask you the usual questions and spit out a project for you. This is just a paste project, so there's nothing really special here. Although it does have one nice little feature in that it supports multi-level namespaces. So this is the sort of thing it'll create. It'll create a namespace package for you. So if you create a package, say pymakeproject a.b.c.d, it'll create all the nested directories for you, each as a namespace package, and put all the files in the correct place. It gives you a few sample tests, some example code, that kind of stuff. Okay, so once you've got your project and you've been working on it for a while, you want to write some documentation. So we have some tools for that too. So this uses Sphinx, of course, and it's driven from the setup.py build Sphinx target. So you run setup.py build Sphinx, and it builds your documentation and runs the autodoc and runs some doc tests as well. Now this is slightly different from standard Sphinx in that it combines API documentation and standalone documentation in the same run. So the first part of it is it runs and autodocs all of your API into an autodoc thing, so it generates little snippets that Sphinx needs to autodoc your modules and your class files, and then it'll build the standalone documentation, things like recipes and user guides and whatnot. It skips anything starting with an underscore, so if you've got private files, you just put an underscore in front of them, and they'll just be dropped from the autodoc. Documentation it generates, this is just a sample at the moment of the current theme. One thing we did with this, though, is because we do a lot of working with NumPy, is we stole their documentation, their docstring format. They have quite a nice little module called NumPyDoc, which is integrated into this as well. So that's an example of what it looks like, where you get nice views on parameters, return types, examples, that kind of stuff. The docstring format itself looks a bit like this. So it is quite verbose, which I agree. But it's also quite nice. If people are working with IDEs, you've got researchers, and they do the current sort of mouse over a function, what does the docstring for this? It means that your docstrings are actually nicely readable as well. And if you've got nice IDEs that read RST, it'll render it to HTML inside the IDE. Also quite nice. So yeah, and it also renders to nice HTML. The actual format of this is in the standard example code that comes from pymakeproject, and there's lots of docs online there. Okay, so moving along, build and deploy tools. So it comes with a few niceties for this as well. You can run setup.py Jenkins, and it'll go and create a build for this project on your Jenkins server. So it looks up the VCS address, much like PyCheckout, and the Jenkins URL that's set in your packagelib.ini will be used to go and either create or update a job on there. It uses a set of 5 minutes. Thank you. Uses a set of standard set of modules. Use Curvature for code coverage, XUnit for test reporting, and the violations plugin for code quality. It just runs through the standard set of setup.py develop, test, build Sphinx, and upload steps. Okay, so what else have we got? The setup.py deploy, which given a path in your packagelib.ini file, creates versioned virtual environments. So you build the thing, you go setup.py deploy, and then it'll create whatever the version number that is. It'll create a directory, a virtual environment in that, and install the package into that and all of its dependencies. It also maintains a current link, so whichever one was the latest one you installed, it will move that link along. It'll also symlink any console scripts into a bin directory if you so desire. Okay, so some of the more experimental features. There's setup.py test egg. What this does is it generates an egg from your package that contains only test code. So some people don't like deploying their test code along with their production code. I just want production code on production. No test code, none of that. So what it does is it basically does the equivalent of running setup.py, all of the code that is required to do what was equivalently setup.py test, including the configuration, builds it into an egg, and gives you a little command line hook called run test. So you create the test egg, and it'll spit it out, and then you install that. At any point later in time, you can then install that test egg, run tests, and the name of the package, and it'll do exactly the same thing as it would have had you run setup.py test on the source code checkout. Now, why would you do this crazy thing? If you have a hotfix to a production install, it's nice to be able to recreate what the development environment was originally without having to go back to source code checkouts for everything. Again, it's slightly experimental. Another slightly experimental thing is the ability to generate new development versions on the fly. So the egg info setup.py build target is the thing that manages package metadata. There's an option to it called ---- new build, and what this will do is it will do the equivalent of pip freeze and then bake that into the requirements of that egg. So it sort of freezes all of the requirements at runtime. And then it queries your PyPy server and figures out what's the next version of this development egg. So what you can do is you can use setup.py egg info ---- new build on every of your CI server builds, and each and every one of them will be kind of linked to each other. And then you kind of guaranteed that all of these things have passed all of their tests, and in a production release you don't have to test anything again. You just turn that development egg into production one, and then you're done. Again, slightly experimental. Okay, so packagelib.testing. Now, I sort of told a little bit of a white lie in the talk brief for this, is that I'd be demonstrating some of this stuff. Unfortunately, my talk was slightly shortened from my original plan, so I'm just going to have to give a bit of a summary here. So packagelib.testing has a bunch of quite useful tools. It has context managers and also py.test fixtures for managing temporary directories, creating virtual environments, and indeed entire packages themselves. One of my favorite features on this is actually the server runners. So what this does is allows you to just basically add a py.test fixture or funcarg into your test, which will start up a server, give you a handle to it, allow you to do all your stuff on it, and then when the test is finished or when the fixture has expired its scope, it will then go away again. They have sort of a save, restore, and teardown hooks into them, and there's implementations for Mongo, Redis, Jenkins, and pyramid server implementations. So if your package is a pyramid server set up within packagelib, it'll allow you to basically run your server within the test and give you a handle to it. There's fixtures also for the Selenium WebDriver, which talk to the pyramid server implementation. So if you have the WebDriver fixture and your pyramid server fixture in the same test, your WebDriver instance will know where to find your pyramid server. So you don't have to do any extra configuration around that. Another part of it is the page objects pattern implementation. Now, page objects are a very cool way of testing web applications. I won't go into the details here because you could do a whole talk on them, basically. But very quickly, it essentially encapsulates an entire web page into a single class with attribute lookups to look for those things on the page. It's a good way of reusing components of tests. So there's an implementation of that in there. There's also a few useful little mocking utils. Okay, quick feature summary. Again, so we've got py-install for installing packages, py-install -dev for dev packages, py-uninstall, which is just like pip uninstall, but it looks the same as the other links. There's py-make-project, there's the plat tool, there's checkout, dependency graphs, and cleanup, which does the equivalent of the end of that resolution phase, cleanup phase, if you want to kick it off manually. There's also the setup.py targets for test, update, build Sphinx, creating jobs on Jenkins, deploying stuff into versioned virtual environments, and creating test-only eggs. A question has actually come up, which is, why would I use this if I'm not working in a company? So I think some of the nice things in there, like the dependency graph viewer, the project templates, and the text, just having a text config file for your metadata is quite nice. That's my favorite bit. I hate having to hack on setup.py files. Okay, so where to from here? This is the interactive bit of the talk. So this kind of sort of depends on you guys, because I respect the Python community's opinions on things. There's far too much fragmentation in the Python packaging world already. I don't want to sort of create yet another standard a la the XKCD comic. There are some features missing from this. Git and Mercurial support should be pretty quick to add in, because it's already using pips, version control, wrappers. And I need a little bit of work to get it installable with pips straight off PyPy. And I'd like to wire in the wheel distribution format, which has come along. So, hands up if you guys think it would be worth finishing this library as it is as a standalone project with all these kind of features installed. Okay, so hands up if you think the ideas here should be kind of split up and broken and implemented in the current packaging tools. Things like dislib and all those other sorts of things. Okay. All right, that's pretty much it for me. Thanks for listening. That's my Twitter. The code's there. Documentation's up there. The API docs will be up as soon as I can figure out why read the docs doesn't like my config file. And there's a Google Groups there. Thanks very much.
Thank you. So, question time.
Well, thank you for this talk, and thank you for going through all the trouble of making this. I think this is great. It's not so much a question as much as like a share where I just want to say that we go through exactly the same problem. The one difference, though, is that I think that people in the Python community, maybe that's just my opinion, are trying to go away from binary.
Yep.
For many reasons. But that was really all.
Yeah, I understand. Like I said, it was an internal kind of policy decision. We wanted binary packages because it just took too long to installing a source package. If you've got lots of C extensions, just to churn through them every time. People want to create and throw away environments quickly, and having source packages just takes too long. And the build server as well, when it's doing 30, 40, 50 builds at a time, it's just a waste of time having to recompile. Even just the PyC compilation takes a while when you're scaling it out to lots and lots and lots of builds all the time. It was really as simple as that. It's just a time thing. I agree that binary packages aren't so good for open source world, but for in-house stuff, it made more sense.
Do you by chance also follow, thanks for the talk, it's really I'm very impressed by all the details also that you try to tackle. You know about PEP 426? That's the recent metadata 2.0?
Yeah.
Yes.
So that's...
It's still changing, so it's not so easy to actually compare against. I just changed something, there was just something major changed last week, so... but how do you think, how far is your setup of CFG apart from what PEP 426 defines?
So a lot of this was kind of developed sort of like mole rat kind of underground, and now we're popping our heads out to see what's changed in the world. We took a view of the world as it was when we were developing, and we went, all right, we've got to make this work now. So we finished it in production, and we sort of left it alone for a while, and now we're seeing what's happening along. So one of my goals for the next week or so is to look at exactly this stuff. Where have all the peps come to? What can I tweak to make it work? So I'm not sure is the answer to that, but I will find out. Yeah, I would not be at all surprised. Anything else?
Any more questions? Okay.
All right.
Thank you very much, Edward.
Thanks a lot.